Hello, everyone. Good morning here from Washington State. It is gloomy and drizzly out here in Washington. Let me just get my screen share up. Apologies in advance as well for my raspy voice. Been having a lot of issues post-COVID, so we'll have to take it slow and see how it goes. So I thought today it would be fun to go in all sorts of directions with this talk. So originally I wanted to go through all possible optimizations of the Bitcoin SHA-256D algorithm, as well as all possible optimizations on ETHASH, as well as some of those design choices that have been made, that we think have been made by the engineers responsible, cryptographically or otherwise. However, I figured we might start elsewhere first and talk a little bit about, mining overall, how it's translated into various design choices, what coins have learned from each other, and some of the hidden techniques that exist in mining that you don't really see or hear about unless you're working in the industry. Give me 2 seconds. There we go. So we've got a little background music to go ahead with this. If anyone wants to YouTube that. So in the beginning, Satoshi, the very first proof of work algorithm that was commercially available, it was SHA-256D. And, everyone was generally happy with that. Though a subset of us were very confused because, well, for a start, you never really doubled your rounds of SHA-256 unless you were worried about length extension attacks. Something that wasn't really possible in Bitcoin with the way it was designed. On top of that, a lot of people, theorized that it was for birthday attacks, which turned out to be wrong. And SHA-256D ended up becoming less secure than SHA-256 as a whole. And so we became all very confused about why Satoshi had made this. Was it just because, SHA-256 was handy and it was standard and he just doubled it because, hey, that'll make it really hard to implement on an ASIC, right? So the algorithm SHA-256D, it's essentially the same. SHA-256 is 64 rounds. We have the breakdown of how many additions, ORs, and XORs it is on a hardware implementation. It's actually not too much. Part of the optimizations available in SHA-256 happens around the fact that you can highly parallelize this, meaning you can have individual, rounds of SHA-256 happening in parallel. And there are a ton of bit shifts in SHA-256, which are essentially free on ASICs. They're free because rather than taking up, an operation or a cycle, they're literally just lines that you route in your design that sort of operate at an angle. So they don't, and they sit next to an array of gates. They're free, they don't take up much die space at all. SHA-256D, on the other hand, again, it's just doubled. We get more die space, but that's about it. And we get more bit shifts. So you get more speed ups and more power savings on an ASIC versus a CPU or a GPU. So everyone was very confused why Satoshi was choosing this. And, because of how parallelizable it was and the sort of speed ups you could get, we quickly moved from CPUs to GPUs to FPGAs in a span of 3 years, which is quite impressive for something that was, essentially just an experiment at the time. As 10 years later, looking back, we start to realize that Satoshi understood that your hardware choice matters just as much as any of your other design choices in your consensus algorithm. So Satoshi references many times throughout all of his postings this concept of specialized farms, server farms, ASIC farms, etc. Specialized farms that are essentially breaking up verification as well as transaction. And we learned that part of his design choices with SHA-256D was really around ensuring that specialization had a path and that you could get these monumental speedups, and also so that you could break out the proof of work piece away from the verification piece. Satoshi imagined, there would be these giant farms that were focused on the verification of the data in the chain, as well as giant farms that were focused on the processing of blocks, and that they would be able to work in harmony, and somehow the business model would work there. Remember, Satoshi wasn't designing, for a cryptocurrency system. He was designing to replace the banking system. He was designing a world financial system. And so he used a lot of, a lot of the traditional knowledge of how banks and businesses operate. But he didn't want it, he wanted specialization. He didn't want it too fast. Quickly in 2009, GPUs started to take a majority of the network away. So they went from 3.5% of the total hash rate to 17.3% in the span of 2 days. And it always makes me laugh that, he wrote on Bitcoin Talk, let's have a gentleman's agreement. Let's just all agree never to use any GPUs and trust each other. Of course, that doesn't really work in reality. But, he also understood that people had to be onboarded into the ecosystem. People needed a way to press a button, just one click, instantly start participating, feel like they were getting a fair share of the rewards, that they weren't disadvantaged, and feeling like Alice and Bob, if they contributed the same amount of computing power, they would get paid the same amount, and that there would be no unfair competition there. So we understood a little bit about the incentives that are required in a proof of work algorithm. So it is all about design. And this is one of the big flaws I've seen over the last 10 years in pretty much every mining algorithm, aside from Bitcoin. Most people are either software developers focusing on the cryptography, which is the wrong way of thinking about it. They're focusing on ASIC resistance, which is also the wrong way to think about it. Or they're trying to think about how can we get outside participants, big banks, etc., to adopt our coin and start using it. Also the wrong way to think about it. You can't focus on one of those areas. Number one, there has to be a migration path through different types of hardware. Number two, what happens with other coins doesn't translate necessarily to your coin. So you can't point at Bitcoin and say, hey, it worked for them, let's go and adopt and use this. And number three, things change over time. And you also don't design for a worldwide system initially. So, Facebook didn't go and design their product to target the whole world. They designed it mostly for Canadian universities very early on. Then they slowly grew and they had a path forward. Most coins today try far too hard to target everyone. And so they start to lose focus. So the important thing to understand is hardware first and foremost creates incentives, not just financial incentives. It creates other kinds of incentives, which we'll go into. Incentives are going to be your tool for user engagement. So it's going to be how you onboard new users, how those users then speak about your coin or speak about your blockchain and talk about it, how they go and spread the word. So early on in a coin's life cycle, your users are your most important asset, because not only are they contributing, but they're going to go in almost like this is the wrong word to use, but I'm going to use it anyway, almost like a pyramid scheme. They're going out and they're recruiting other people to come in, join in. They're spreading the gospel, as it were. So you're relying on users to reach other parts of our network that you don't have access to and bring people in. Hardware is one of the key parts of that. So specialization is what a lot of people try and chase when they're designing for a proof of work algorithm. They start to say, hey, let's just go and design our proof of work algorithm to target an ASIC, because that means that these people will have skin in the game, right? And in theory, that works on paper. In reality, it doesn't really work. So in a lot of the arguments I have, people tell me that, hey, Kristy, if someone has an ASIC, it means that they're going to keep that ASIC on and participate in the network. They'll never turn it off. That's not what happens at all. People spin up and down ASICs, just like they would a GPU or a CPU. They get bored and they go and mine other coins that share an algorithm, or they just decide to exit mining one day. The ASIC just becomes a device, and, it's a device that's sort of a portal to mining, but it doesn't change the user's behavior in any way, shape, or form. Moreover, humans can't really be bottled into one sort of bucket. You can't just say, hey, all humans will act rationally. An important design principle to understand, and one of the things we've been learning over the years, is that everything is an ASIC. So to a hardware designer, everything's an ASIC. Any algorithm that can run on a CPU ASIC, a GPU ASIC, or an FPGA ASIC can end up having a specialized design created for it. So it's really naive to say that you can be ASIC resistant. Instead, the correct approach is, you can say that, hey, this is my targeted platform and I've optimized for that. And what you want to do is make sure that the efficiency gap, which is something that you're always tuning for. So the difference between your target platform and a specialized design isn't wide enough that it gives an unfair advantage. You want to ensure that, if Alice has a good old CPU and she contributes 1 hour's worth of processing power, Bob doesn't have a 100x advantage over her with his ASIC. He only has a maximum of 2 to 3x advantage. It keeps things fair and it ensures both participants are happy. And the other thing to understand is when people, talk about they're wanting to resist ASICs, they actually have no problem with the hardware. Most people don't even know the difference between a CPU and a GPU, aside from, hey, one helps my computer run and one helps my computer play games. Hardware wise, they don't really understand the difference. What people really are trying to articulate is they're trying to say they want their network as decentralized as possible, and they want as many participants in their network as possible. So I want to walk through a little bit about ETHASH. ETHASH was an anti-ASIC algorithm that tried to fulfill these principles. So ETHASH, or Ethereum in general, looked at Bitcoin and they said, here are the things we don't like about Bitcoin. It didn't like the fact that Bitcoin pursued specialization so far ahead in advance. It considered ASICs a scourge. Most of this happened due to the behavior in the Bitcoin, I would say, community. So during 2014 to, I would say, 2016, it was found that a lot of the hardware manufacturers were not playing cleanly. They were playing dirty. So hardware manufacturers learned that it was far better for them as a business to simply take users' money, pre-build a lot of these devices, mine with them for 3 to 4 months, claim delays on getting materials, and then eventually ship it out when they'd ROI'd those devices for themselves, or they'd half ROI'd. So they got some amount of money. They called this a testing phase, but it essentially allowed Bitmain to get Bitmain, Canaan, Silicon, etc., to get double their money for each device produced. That was great. That also left a lot of sour taste in many people's mouths. NVIDIA doesn't use your GPU for 4 months and then ships it to you in a box as new. Nintendo doesn't play on your Switch and then ships it to you as brand new. So, people were buying brand new devices and they got very disheartened when suddenly these devices ended up in their hands with issues around dislodged chips, heatsink issues, the heatsink was loose, dust. I remember back in the day getting a shipment of ASICs that we couldn't even install because they were just caked with so much dust. So it was just generally considered really unfair. The other issue that was happening was manufacturers were starting to compete with each other through nefarious means. So manufacturers would start to buy out each other's silicon space. So in the traditional world in GPUs and CPUs, there are rules and regulations around doing that kind of thing. In some cases, and David Vorick detailed this really well in his SIA blog post. In some cases, Bitmain would actually try and buy out or threaten or intimidate, suppliers. So, if one of their competitors was using a certain PSU supplier, Bitmain would either go in and purchase all of the PSUs possible, or they would intimidate them and say, hey, shut down operations, don't serve this customer, otherwise we won't do business with you anymore. Now, Bitmain has learned from a lot of those mistakes, and I attribute a lot of this due to the fact that they were a young, naive business. And I look back at, AMD and NVIDIA and Intel's behavior back in the 90s, they also did a lot of the same mistakes. until rules and regulations came in place and businesses matured and grew. And also the founders grew and matured. The other issue that ETHASH had was they desired their network to be as decentralized as possible. So one of the unfortunate side effects about adopting ASICs is your hardware becomes tightly concentrated wherever the supply chains are. We can't get away from this in proof of work at all. We're inherently reliant on some form of hardware. In proof of stake as well, and I'll go into that a little later, we are still reliant on hardware. So for Bitcoin, people became very reliant on the manufacturers that had made it out of, the 2011 to 2013 rut. And for those of you who don't know, during that time period, it was a source of fierce competition. So companies like BioStar, Asus, MSI were actually producing ASICs too. Not many people know about that, but they were producing it. Wasn't very optimal. You had companies like Butterfly Labs. You had all sorts of operations in China that were spinning up and building these Bitcoin ASICs because the algorithm is so simple and so easy that you don't really need a lot of hardware experience to build a functioning SHA-256D chip. You just need to understand a little bit about FPGA program. You need to have a little bit of experience in electrical engineering, and that's about it. And most of the battle during that time period was fought on process node. So people were just competing for smaller and smaller and smaller process nodes to ensure that they had the best power efficiency. There were real algorithmic improvements until we came to ASIC boost, which was the source of a lot of controversy. An ASIC boost was something that was a way of mangling a certain part of the SHA-256D operations and part of the nonce. It had two forms. One was called overt, one was called covert. But basically it involved mangling parts of the Bitcoin transaction, and you were able to get speed ups. And the basic math is, you would be able to perform 4 operations, or in some cases 8 operations, where it would take the power or the energy consumption of 1. And manufacturers did something really dirty here. They kept this in their designs, so in their chips, and they only enabled it for their own personal mining farms. So this sat in the hardware for almost 4 years until someone publicly uncovered it. Big scandal broke out. Patents were involved. Patent trolling was involved. And then finally, I think it was in 2018, Brains, a well-known Bitcoin mining pool operator, released their open source implementation of ASIC Boost and brought it to the world. But hardware manufacturers sat in this hidden secret and basically said, hey, we're going to use customers' money to fund our development of hardware. We're going to keep this hidden secret optimization all for ourselves. And we're only going to allow it to be used when we're personally mining. So that left a lot of sour taste in people's mouths. ETHASH was, hey, let's go and be free for everyone. Let's ensure that we target the most widely available commodity hardware, which at the time was GPUs. Remember, back in Satoshi's era, in 2009, GPUs were still mostly used for gaming. There was a tipping point in October 2009 where GPUs transformed into general purpose parallel computing devices. And that partly happened with NVIDIA's Fermi architecture and CUDA. It partly happened with the adoption of floating point, according to the IEEE standard. Partly happened, due to some of the hardware tricks they had done. And AMD was playing catch up at this time still. But until that point, back in 2009, GPUs were really just seen for graphics. So, that's what ETHASH adopted. So here's the general flow of ETHASH for those of you who aren't familiar with it. It looks quite elegant, and it is. Part of its ASIC resistance is, and I'm not sure if people can see my cursor, but it is here in the DAG. So the DAG is essentially a global lookup table, and you have to do many reads and many writes moving in and out and in and out. And your speed at which you can do this becomes limited by your memory bandwidth. So one thing that GPUs have an advantage of over FPGAs, again at the time, and over CPUs is memory bandwidth. They have a lot of memory strung onto their board, which their little GPU ASIC can access. And so that made ETHASH really, really simple in theory to be ASIC resistant. Now, at this point as well, a lot wasn't understood about what could be done with specialized hardware and memory chips. So Google had not announced their TPU yet. There wasn't a lot of hardware advancements in memory. Hell, memory was just starting to take off. We just had the G5 specification sort of finalized. And I think at that time, we were still sitting on 2 GB of memory for GPU cards. Meanwhile, today in 2020, you can buy a GPU card with 128 GB of memory. So it's kind of insane how much we've jumped in a very short distance. And so essentially, you take the header and you're taking your nonce, you're moving it through Ketchak, you're splitting it into, you have an init digest of 64 bytes, which partly gets fed into the DAG, and then it cycles through 64 times, FNV'd every step of the way. And then your digest is also copied over and put into another round of Ketchak 256, where it's combined with another 64 bytes of whatever you've just mixed out of your DAG. And so there's a trade-off, and if you think of it visually, there's almost an elegant trade-off of every time you do a memory access, you do a compute access step. This is very hard to implement into a fixed function ASIC in theory, because memory controllers, the things that allow memory to work with with some sort of core, are the intellectual property of both AMD and NVIDIA. So GDDR5 memory controllers weren't publicly available. That's changed today in 2020. When we moved from GDDR5 to GDDR6, it became open source. And so now anyone in the world can go and download the specification and the standard, make their own improvements, and produce their own memory controller. So, that was Ethereum's incentives. GPU good, ASIC bad. Where that all went wrong is in a few areas. Number one, Ethereum thought that people would not hoard. Turns out that if anyone in the world can hoard things, they will. If there's a financial benefit to hoarding things, people will do it. Case in point, COVID and toilet paper. So humans aren't really rational actors. Moreover, the skin in the game argument falls apart when you're trying to talk about both GPUs and ASICs. So today in 2020, there is a huge amount of GPU computing power whose sole purpose is to mine Ethereum. It's never going to be sold out into any other vertical. Part of this has to do with the fact that mining rigs are not translatable to HPC. So there's differences in PCIe bandwidth. There's differences in what the cards can do. There's differences in levels of security. So many miners dip into the firmware of their GPU card and make tweaks. You cannot do that in, in a production level, financial model, because that's how you get errors, and you want to decrease your chance of errors. Proof of work, we don't really care if we have errors, we just move on to the next hash. So there's a ton of GPU computing power that has essentially become the ASIC for Ethereum. It's not moving, it's never going anywhere. It is sadly hoarded in large concentration. A lot of that has eased over in the last 2 years, but in 2017, there was a large rush to purchase as many GPU components as possible to build your own cards. Many people think that was miners. In fact, it was actually 2 manufacturers. It was Bitmain and at the time InnoSilicon that went on a race to purchase as much memory as they could because they saw an impending gold rush. And they were able to flip memory, and they were also able to use this to mine Ethereum for themselves. Second thing that Ethereum didn't understand very well is when people finally started to build ASICs for their chain, they assumed that they would just be able to give up and that ASICs would just start flowing in. That isn't really how it works. You can't build your own supply chains. So Bitcoin is very unique. It was right time, right place. In the early days, it was mostly hardware engineers cryptographers and researchers who were all nerding out together. And the actual design of an ASIC took place in an open source environment. So if you go back through a lot of the old archives on Bitcoin Talk, you're going to see people sharing their FPGA designs, sharing a lot of their VHDL, sharing a lot of their circuit board designs that they're very excited about. You're going to see lots of posts from Bitfury. You're going to see lots of posts from some of the other chip manufacturers that are working with their customers to iterate and try out new things on board designs, new things on controllers, new things on communication channels. Because there weren't a lot of financial incentives yet to mining Bitcoin because it was essentially worth nothing, this became more of a fun hobby. And when it came time for Bitmain in 2013 to build on top of all of that, they had a wealth of knowledge that they could pull from, meaning that they could essentially start up their business quite fast. They didn't have to do a lot of work or research, and the supply chain was essentially built for them. The other thing is that they didn't need to sell out to many countries all at once. Bitcoin did not have a lot of regulation, and most of the mining was concentrated in China because that was, that was where Bitcoin really took off early on because of the concentration of hardware engineers. It also took off in the US. And US entities like Butterfly Labs, etc., were able to sell out. The third thing is that most proof of work designers are trying to optimize for hash rate. This is a very incorrect metric. So in all sorts of proof of work algorithms, energy spent is the only important metric you care about. It's about ensuring that you have some sort of capex cost, so some sort of hardware cost, plus an ongoing cost, your OpEx. You're not competing for high scores. Hash rate could be 1, it could be 10, it could be 100. The security of your network is defined by how many participants you have, not by the speed of your hashes. This is really important to understand, and it's something where I see a lot of proof of work designers fall flat because they're all trying to, chase, oh, look, we've managed to save a bunch of energy here and our hash rate has doubled. That, only makes sense if your coin, if you're actually building an ASIC and you're trying to chase profits. It doesn't make sense from a design perspective. So again, proof of work is about capturing as much hardware cost as possible. Now, Bitcoin wasn't able to do this on CPUs, GPUs, or FPGAs. In fact, it captured none of the hardware cost, hence why ASICs made sense, and hence why you see today giant boards of 128 or more chips of Bitcoin ASICs. That's capturing the cost. With ETHASH, it's only capturing about 50 to 60% of a GPU's cost. So that means if you're going to go and design, be an ASIC designer, you just have to shave off that 40% of the GPU that is not utilized. That's roughly how it works. And so the other thing that I've realized is that proof of work designers always think that their players are going to their miners are going to act according to economical theory. So I often think that designing a proof of work algorithm is a little like DMing. You have a ton of people that will do stuff for financial gain, sure, but you also have a ton of people who would just do things to cause chaos. So let's look at some of the historical examples. Back in Bitcoin's history with mining farms, there would be mining farms set up to do block withholding attacks or even shadow mining attacks. This had nothing to do with financial gain. It was simply because, one, they could do it, two, because they wanted to do it. We also have history of 51% attacks happening that haven't actually resulted in financial harm, meaning they've caused damage to the network, then they've returned the money. Oftentimes this is miners just trying to see, can they pull this off? You've had pools in Zcash censoring some transactions. You've had miners doing really, really weird stuff with their hardware. You've even had miners that have decided to financially harm themselves, meaning they will mine a less profitable fork of Bitcoin because they either religiously believe in the coin or just to spite the main coin. They say, hey, Bitcoin, I don't agree with your ideas. I don't agree with this specific BIP. I'm going to mine this other fork out of spite. It doesn't benefit them economically, but they do it. You even have large mining operations that will send all of their hash rate to a brand new startup coin. that is worth nothing. It doesn't work on any exchange, etc. So it's important to understand miners aren't always rational beings. They don't fit into a nice little box. When you're designing for them and your proof of work algorithm is getting designed for them, you have to think about the coin as a biome as a whole. And so I also want to talk a little bit about mining myths. So as we get through this talk, some of you might be jumping online and looking into mining to learn more. There's a lot of myths out there, and it has become exaggerated over the last 2 years, and it's very frustrating. My favorite one is miner capitulation. So this is the theory where miners are just going to give up because the price is so low and they're going to dump all their hardware. It literally, capitulation, literally, it means to surrender. And so the theory goes that, you know, if Bitcoin hits a very low price or whatever coin hits a certain price threshold, miners will just push a button and they will turn off their operations. That doesn't work in reality. Number one, miners, large-scale miners, medium-scale miners, even some small miners, have electricity minimums they have to meet. So they get a really great deal on power from the power company only because they have agreed to consume so much over a certain time period. The time period is usually a minimum of 2 years here in the US, though I have seen some deals for a year, and the best kinds of prices are a 30-year commitment. So that's 30 years you're agreeing to consume some very large number of energy. That means that you can't suddenly just, you know, turn off your operation when things aren't going your way. Moreover, it is actually a lot of expenditure on the transformers and all of the electrical equipment in a farm if you're just constantly spinning up and spinning down your hardware. So I've read one research report, which I think, thankfully, I think it was CoinDesk. I think they've removed it now, but it was a research report saying that, you know, there was a theory that miners would eventually be turning on and off their operations according to micro swings in Bitcoin price. That doesn't work. It's the same reason why you have all these data centers around the world with large CPU servers and GPU servers that are always running 24/7, because it is taxing on the electrical equipment to turn it on and off, and it actually saves the money to just keep it running versus turning it on and off and waiting for that boot up time. So it just doesn't work. The second big myth is that miners are dumping. So the theory goes that, you know, miners quickly dump all of their coins and crash the Bitcoin price. So mining operations are businesses. Miners aren't stupid. They don't dump money willy-nilly. A lot of them today actually have intense accounting divisions. They have dedicated FP&A people that just do analysis 24/7. So they're thinking about, you know, when should we buy and sell historically? What has it been? They have sophisticated buy and sell strategies as well. So a lot of the miners pre-halving, at least as it pertained to Bitcoin, and even before ASICs launched on Zcash, a lot of these mining farms began to develop strategies. So in case of the halving, people, I saw a lot of private companies trying to do a 40% hold, 60% sell strategy, where, you know, at the end of every week, they would hold 40% of their earnings just because they believed the Bitcoin price was going to go up after. A public company, meanwhile, might not be able to do any gambling whatsoever. So they're going to have to sell on a regular cycle according to whatever, you know, their CEO, compliance, and shareholders are expecting. So miners actually do have sophisticated operations. One of the fun things you can do is if you analyze exchanges and you analyze regional swings in price, you can correlate it with some of the electricity bills that are happening in a specific region. So one of the funds that I used to consult for back in 2018 did a lot of fun work with this. They would analyze around the US when miners were going to pay their bills, and they would correlate that with roughly the percent of the mining farm they would have, and they would wait to take action against their trade on Bittrex or Coinbase, whatever it was. So that was pretty cool. The other thing is that miners chase profits. So again, this doesn't work in theory. Um, as I talked about, you've got two buckets of miners. You've got nomadic and you've got tribalistic. Nomadic miners are, miners that are going to move from coin to coin and chase it for profit. And they are most likely to actually jump off contributing to your network in any way, shape, or form. So you don't actually want to be competing or trying to get the attention of nomadic miners. Ignore those. Tribalistic miners are what you want. So tribalistic miners are what you should be designing for. These are people that are going to invest all of their time and energy into educating people about your specific blockchain. They're going to go champion it. They're going to help out where they can because they're passionate about it. They're going to invest the most money within their means. And the whole point of all of these different coins is really that you're all competing for the same base of tribalistic miners. So there's a finite amount of people that are going to actually use cryptocurrency right now, today in 2020. And it's a coin's job to compete on all of the different feature sets to attract some of these tribalists. Now, a tribalist can sit in many different coins at once, but generally, when it comes to proof of work, they're only going to have one or two they pick, usually one CPU coin and one GPU or ASIC coin. They're not going to have lots that they're invested in. So a lot of these coins have to compete on features. Ethereum's done a great job of this. Miners jump in, they can earn some Ethereum, and then they can start contributing in DeFi. They can start playing some games. They can start, interacting with the network. They can bid on Gitcoin grants. So Ethereum has a whole ecosystem dedicated to what can you do with the Ether you've mined. Bitcoin as well has this, but they've gone down a different route of just get stores to adopt it. So a lot of people want to get into mining Bitcoin because they see it as an alternate investment. Those are really great ways to attract the tribalists. The last myth, which is very weird given a lot of the news that comes out, is I hear, especially today from a lot of proof of work designers, that big players don't mine. Big players will never be interested in crypto. So Blockstream is probably the most famous for this. They have Reid Hoffman and Fidelity. I think it's Fidelity's Bitcoin division, but they have Fidelity with them. Blockstream's just one example. You've got large companies like Xilinx, like Intel, like NVIDIA, and like AMD that are either watching cryptocurrency as a whole closely, or they are watching the mining space. Hell, AMD has just done a joint venture with, I think it was called Halo Investments, to build what they call Web3 Cloud, which is a data center just for, it's partly for staking, partly for rendering, partly for a bunch of other things. So you do have big companies that are very interested in mining, and they're not treating this as, oh, we're going to make a ton of money. They're actually treating this as, hey, we believe in the principle and the value of blockchain, and we want to contribute in the only way we can, which is usually through dedicating hardware. It's the easiest way. You also have a ton of bigger companies that are currently exploring how they can accelerate proof of work, not because they want to sell more hardware. I mean, yes, that's one of the benefits, but because they genuinely believe in the mission of blockchain. They want to see alternate use cases. So a big one that I'm seeing today on my end is seeing a lot of companies are dedicating resources to figuring out how can they accelerate zero knowledge proofs on hardware. How can they build dedicated servers or dedicated farms just for ZK proof transactions, and that's it. And it's not because they're going to make money now. In fact, there's absolutely no money they could make now. There is no payout to their resources now, but they're betting that, this will be the adopter or the driver for a Bank of America or for a bigger company. Then I wanted to also touch on pools. Wait, that's the wrong pool. This one. So this is another common concern, and one of the concerns you need to have in your proof algorithm. It's hash rate distribution. So you are always going to need some sort of a pool. A pool is essentially a work provider. They are going to be the ones that are crafting the blocks for your blockchain, and they're going to be serving, work packets to miners. Many proof of work designers pretend that pools don't exist and that miners are naturally going to run their own node, connect to the node, and craft their own blocks. That will never happen because, miners might not be lazy, but they are generally not that technical. and it's a lot of work and a lot of unnecessary overhead. So one of our issues right now is in pools. Hash rate is mostly concentrated in China. So for Bitcoin, it is, I think today it's roughly 67 to 68% post halving that's concentrated in China. Now, is that an issue? Well, it's not really, and it also is. So it means that the governments can interfere with your specific cryptocurrency if they want. This is one of the downsides to tying yourself to proof of work. So if the government really wants to interfere and they have a majority, if the majority of the hash rate sits in their country, they could try and take away your capex, or they could try and intimidate the pools to censor some transactions, or they could try and gain whatever intelligence or insight they can into some of these transactions. Thankfully, not possible with Zcash, not possible with Monero. Still a bit of a concern with Bitcoin, but things are being done to fix that. However, it's important to understand the only part of this that matters is where your capex is located. So the benefit of proof of work is that your capex is physical. So in a proof of stake environment, your capex, your stake in the network, is a digital coin. That's not necessarily good. That's not necessarily bad either. It just means there are different threat vectors. Whereas in a proof of work environment, your stake in the network is physical. Meaning if someone wants to go and throw a virus on my ASICs, I can still unplug them from the network, clean them up, reconnect them. And if I decide to exit the network, or if I decide, that a pool is being mean to me, I still haven't lost my whole stake in the network. It's still sitting with me. Most of it's in my hardware. And I can also freely move that hardware around. So this is one of the important things to think about when you're designing a proof of work algorithm. You want to ensure that your hardware is distributed as possible. This can happen in ASICs. It has happened with Bitcoin ASICs. It's taken a while. It will not happen with any other ASIC unless it has the kind of TAM or market cap for Bitcoin. So today we have to think about, okay, what kind of supply chains can I ride on? Monero rides on top of CPUs. People that are adopting ETHASH, ProgPow, CorePow, these GPU-tuned algorithms are adopting GPUs and riding on their supply chains, and these are global. These are $350 million plus supply chains. Sorry, I should clarify. $350 million per month supply chains, often more. Sometimes GPU manufacturers do $4 to $8 billion worth of hardware per quarter. So these are, multi-billion-dollar supply chains that distribute hardware to the whole world in areas where an ASIC manufacturer could never even think to distribute. The other thing I want to touch on today, and something that I think a few of you are excited about, is nuances. So this is a field of research I'm particularly excited about as it relates to mining strategy. It's also a little concerning because it does show it leaks a lot to the nature of miners, the nature of the hardware they're using. And yeah, figured I'd just spread some awareness about it. And it's one of the big flaws in proof of work design as well. So because we're so reliant on pools to serve our work, we end up finding over time that pools have very specific nonce search strategies that they send out to the ecosystem. And this means that, instead of what you're thinking, which is, any nonce should have an equal opportunity of winning, turns out that pools concentrate around searching only specific brackets or buckets of a nonce. That ends up giving this really cool pattern we see here. So these dates are actually lined up with Zcash, an ASIC resistant algorithm for the ASIC announcements. We see this pattern here, which is generally sparse, which is, that was a pool serving nonces from anywhere in the range. And then it starts getting concentrated. We see this big concentration here down towards the bottom of the X and Y axes. This is because miners aren't searching above a certain nonce value, so they're all concentrating here. Generally, that's because either, number one, the difficulty is very low, or it's a sign of CPU mining. When the first ASIC gets released, we see suddenly a wave of ASICs, and we see this distinct comb pattern. And this is because there are now so many pools that are competing for the ASICs. They're trying to ensure that their work packages don't overlap with another pool's work packages. It's actually kind of beautiful and kind of cool. So this kind of nonce analysis also has another hidden benefit. It turns out that every single ASIC that is designed has a unique fingerprint, and it has to do with how work passes from chip to chip. So if you know the physical makeup of the hardware, and if you know a little bit about how the algorithm executes on the hardware, you can fingerprint that machine and you can track how many of it exists on a specific chain, and how much of the network that specific machine has, which is pretty cool. Here's Ravencoin as another great example. So where we see this nice little vertical blow up, and we see sort of a vertical waterfall pattern, that's actually due to Ravencoin's block times blowing up, so it has nothing to do with ASICs. As we get a little bit closer to 2019, we start to see this distinct banding. This has to do with the number of hash boards in the ASIC miner that was sitting on Ravencoin and how it processes work. Turns out it skips certain areas of the nonce that it either can't serve, it either can't move towards the next chip with its work package without having an overlap or having a signal issue, or the pools simply have decided that it's not as efficient. And statistically, miners aren't earning, enough rewards from that certain nonce range, which is pretty cool. And then Ravencoin forks, and again, we see this comb pattern starting to happen. So now it's much more dense, much more tightly concentrated. It again has to do with how the algorithm has translated on the ASIC. So something really cool is Ravencoin's very first ASIC was actually made up of eFPGA fabric. It's the first known use case of its kind. So eFPGA fabric is sort of like a hybrid between an ASIC and an FPGA. You get all of the power savings that come from an ASIC package, and you get the form factor of an ASIC chip, but you get some of the programmability and flexibility of an FPGA. You are not limited by your architecture. Instead, you're just limited by the size of the die. However, the trade-off is you can only reprogram it so many times. So Ravencoin was an algorithm that, imagine it visually as 16 different blocks, and it's 16 rolls of the dice that get to choose what order you hash through those blocks in. And so in the very first eFPGA design, they were able to break this up to where one algorithm was on one chip. Then once it's forked again, they've had to ensure that two algorithms share one chip. Hence you get these really tightly concentrated bands. So that's pretty cool. And this one's Monero, which is probably the most famous. It's had 2 research reports done about it. So Monero was interesting. They claimed ASIC resistance from the get-go, and it turns out that ASICs were on their network, right after they launched. So this very distinct banding pattern we see here has to do with how work is flowing through the chips again. And they were on the network for almost, I think it was a year and a half to 2 years before anyone noticed. What is interesting, however, is that after Monero forks, we see that this pattern still carries over. Then we see a new generation of ASIC here, where you see that really tightly correlated pink bands. And then they fork again. There's still one single ASIC type, and we haven't found that it's one of the commercially available ones. It's most likely a specific unit that either Bitmain or Baikal has made. There's one specific ASIC type carrying over until the RandomX fork, where it suddenly disappears. So it's pretty cool to be able to see this finally. Something else we can do is we can actually attribute weight to these values. So we can look at all of the nonces over time. We can run a bunch of Markov chain simulations to figure out, okay, what percentage of the network does this device contribute? So, was Monero 90% ASICs at a certain point in time? And this brings a lot of transparency to a proof of work ecosystem that otherwise is historically murky. So to summarize, you can always build specialized hardware, but you can make a GPU or a CPU your preferred ASIC with your design. There are some reasons why you should, there are some reasons why you shouldn't. Bitcoin should never move from its design. It has perfectly set up its own supply chains, and it's set up an ecosystem of companies that are now financially committed to mining, which is great. And finally, some other things to consider when you're designing your proof of work algorithm or even your blockchain. So you have to think about location. Too often, and I see this in a lot of blockchain projects, they're trying to change the world. They're trying to get everyone in the world to come to them. You have to design your algorithm first and foremost, and also your whole product for where your users are going to be initially concentrated. So start small. Number two, you have to design for KYC and compliance. So it's a bit of a myth that you have to sacrifice privacy to get compliance. Your infrastructure of a proof of work, so your pools and your miners need to be built with public companies in mind, meaning that they can show their auditors, hey, I sent an hour's worth of hash rate and I got paid for an hour's worth of hash rate. We don't have good tools today built in place, and this is why a lot of the big companies still and auditors are still very aggressive against proof of work. If we can figure out that piece, and that really just takes pools and miners working together, if we can figure out that piece, we're going to see a lot more adoption on proof of work as a whole. Talk to professionals. Proof of work has very little to do with cryptography. Use whatever hash you like, just don't make claims when it comes to do with hardware. If you want to capture, a majority of hardware costs, or if you want to make your proof of work algorithm for a specific hardware type, go and talk to someone who actually works in the silicon day to day. And I touched on this before, but proof of stake, it is another form of proof of work in that you're still having a stake in the network. Or I guess rather a better way of phrasing that, this is proof of work is a form of proof of stake. You do have stake in the network as a miner. You have physical devices. You often have infrastructure as well. All you're doing is trading, physical for digital. And there are reasons why you might want to use those in parallel, or there are reasons why you might want to move to a proof of stake model. And you shouldn't just look at proof of stake and think, oh my God, what's going on here? So in a lot of countries where it is impossible to get your hands on hardware, and this happens in a few of them, it happens in places in Africa, and it happens in some of the places, some of the countries that we're not allowed to do business with in the US, Iran, for example. Proof of stake is a better model there, and it will get more adoption for some of those countries. Whereas in proof of work, you're going to get concentration wherever the hardware sits. So mostly concentration in the US and China. All right, I've done a lot of talking, and I am almost out of breath. So I figured I'd open it to if anyone has questions.
Thank you very, 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 very much. There is a bunch of questions in the chat. I think that's probably the best way to, if you could read them and answer them.
Yeah, let me just open that up. Give me 2 seconds. Oh boy. Oh boy. There it is.
So maybe I can start with the first question, which was actually a question. There was a comment about if your miners still mining empty blocks, and I wonder what would be your take on the reason why they're doing so.
Partially they're mining empty blocks. For one, because they want to craft their own blocks and they need a transaction to fill it. Number two, there is some advantage with pulling off. God, it's not flash attack, which I'm trying to say.
Flash loan.
Yes, that's the one. So there is some advantage to that. Partly it's just because they need a transaction to fill their block. It is also due, and I've seen this in some of my farms, where the block crafter, as you call it, the script that's responsible for that part of your pool infrastructure, it just hasn't been optimized. So it doesn't actually look for what transaction can I get. It just throws in whatever it can. And then you do have miners doing it just for spite or just because they can, or just because, you know, they want to learn more about the network and figure out, can they do this? Every step of the way, miners are going to want to bend the rules, because just like when you're running a when you're running a D&D game, your players are going to try and break the rules. They're going to try and test you. It's no different in proof of work. So you have some, you know, you have some beneficial reasons, you have some technical reasons, and you also have some psychological reasons why miners are doing that. And yes, you're right. You're right that empty blocks can be faster to propagate. Again, this is just, you know, they need to move from this block to the next. Sometimes when we're trying to help specific companies accelerate their transaction, I know one of my farms will just quickly mine some empty blocks so that they can get the specific, you know, fit of transactions that they want. Nonce analysis, Daniel, to answer your question, nonce analysis does provide information about CPUs, GPUs, and FPGAs. So it just so happens that with ASICs, it's easier. The signal is strongest. With GPUs and CPUs, what you're actually going for, instead of the hardware, you're going for the software instead. So we did a report on this for Ethereum specifically, where we were able to fingerprint Claymore, which is one of the I would say the most well-known GPU mining software. We were able to fingerprint his dev fee. And what he does, it's actually pretty clever. He fixes specific bits of the whole nonce to 0. Specifically, it's bit 33, 34, 35, etc., incrementing according to his different version releases. So he fixes these to see how many devices are currently using his miner and cross-reference that with the dev fee he is getting to see, you know, without trusting anyone, is he getting paid what he is owed? So that was pretty cool. When it comes to FPGAs, the best way to do this is a two-prong attack. So FPGAs, depending on their implementation, will have banding, or if they have a dev fee, you can track that instead. Today, a lot of the developers are trying to get around nonce analysis, meaning they're trying to randomize their strategies as much as possible. The great thing is that, as many of the cryptographers might know on the call, there's really no such thing as true randomness. And as long as we have enough data, we can iterate this over, you know, 1,000 different iterations, or even 100,000, and we can end up getting a very concentrated signal. And miners will naturally congregate around certain nonce search strategies just because they're more efficient. At least mining developers will. So you can locate your supply chain anywhere you want. The trick is that you need to not build it yourself. So if you want to go and be an ASIC developer today, say let's go take a I don't know say we want to go build an ASIC for Monkey Coin. So the first thing we're going to do is, instead of trying to go and source all the components ourselves and source, you know, our own PSUs, we're going to go work with either Avnet, Arrow Electronics, Future Electronics, or there is a fourth one. I think they're Digilent. So these guys, these four, are what's known as component suppliers. They're worldwide. They serve every single country, and their whole job is literally just to go and price components and sell them to AMD, NVIDIA, Intel, or anyone who needs access to those components. That's their whole job. They're component brokers. They're all public companies. Again, they're based in every single country. So you go to them with your whole BOM and your proposed implementation. You say, this is what I need. I need this, and I need it on a set schedule. So I need to produce, you know, 200 units every 3 months. And they go and build you a BOM and a proposal according to 200 units every 3 months. Even better, they can even handle shipping and warranty for you. And so whenever you want to go and turn your hobbyist PCB project to something, you know, that is at scale, this is the route that we take. The mining ecosystem didn't adopt this because specifically for Bitmain, it made much more sense to just do it in China. So you have to look at the history of the founders. They come from the hardware world, And in China, it's a lot easier to just source these components yourself. You can literally just pop down the street and you can start, talking with one of the manufacturers about, getting so many chips or getting so many components. Now, because Bitmain controls all of their supply chain, they can nickel and dime and they can make a profit on not just the whole machine itself, but the individual components. So it essentially becomes another business model for them. It only makes sense when you're at a very large scale. And we have to remember that for a company like Bitmain, they are not just crypto mining. They're also AI. They have a huge AI division, a huge team of research engineers dedicated to artificial intelligence, and they have hardware that exists outside crypto. So having a supply chain that is their own, it's custom built for their operations makes sense. So anyone can go and make their own ASIC today. Most people just don't know where to start. And I think that has a lot to do with the fact that it's not really well known. You can't go online and figure out, okay, how do I go and get my PCB made? It takes some time and some learning. I'm very sorry for being quiet, Mork. That is partly due to COVID. Sorry about that. And for Steve, so all ProgPal does, it's mostly it's designed for GPU architecture from the ground up. So GPUs really like 32-bit operations. So we've designed it for a lot of that. They don't do too well in 64-bit. CPUs do, however. The other thing is that GPUs prefer certain types of memory accesses. And we ensure that there's, if you think of it visually, that every time we access the core, we're accessing enough of the memory in parallel. We also try and add as much random math as possible in a loop. Part of this is due to the fact that if you want to go and make an ASIC for ETHASH, all you need to do is have really great memory architecture. You don't need to worry about anything else because essentially the bottleneck is memory. The core of the GPU isn't used. So you can go and scrap that entirely and you can offload Ketchak to a very, very tiny core and FNV to a very tiny core. So all of that compute stuff for ETHASH just sits on its own little die and you can just stream the data. Memory is, the thing that you're building for. In ProgPal, if you want to go and build a ProgPal ASIC, you need to make sure that your memory is just as powerful as your core. And it becomes this balance between the two. There's also some things in there about, like I said, which type of memory we access. And the other advantage that we have when developing GPUs is that GPU architecture has to be the same. I forget what governing body it is, but essentially you have to be able to take some OpenCL code, dev for OpenCL, and have it perform within a certain factor, the same on an AMD card as you would a NVIDIA card. Now, there are certain advantages you can get on either type of hardware. We don't use any of those operators. We stay away from we call them ISAs, so instruction-specific architecture. We stay away from all of those in ProgPal, meaning, AMD is not going to get an advantage over a certain operation over NVIDIA, but the architecture remains the same. And thus what's happening is that NVIDIA and AMD cards are now just contributing on their base hardware performance. And ProgPal ends up mimicking GPU games and benchmarking GPU games more than it does with how you've traditionally benchmarked mining algorithms. Alex, what blockchain.com offers is kind of okay. Sadly, there is not a lot of good resources for visualizing anything in mining. So here's what I've learned, and I'm really disappointed about it. It seems like, for the last 8 years, it was really just miners doing their mining thing. There's a lot of tools that are built internally within companies, but they're never shared to the outside world. As researchers and news and media has started to get involved, they're hyper-focused on Bitcoin mining, and they're building tools to help them talk about things or write better reports. And some of those tools they're starting to share. A great example is Coinmetrics. Great example is CoinDesk and their research reports. However, this has only just happened in the last year. There is still not a lot of focus on building great block explorers, there's still not a lot of focus on building, you know, analysis of what's actually in blocks. It's just not a very a fun user workflow. So yeah, right now there's not a lot. If you want to look at mining activity, it's really just scraping. You have to scrape the block explorer for your favorite coin and format that data yourself. There is a great business model and a great opportunity for someone to come in and make a product out of that. And then, you know, their business model would essentially be selling that data. You have a free tier, but you sell that data to funds. You sell that data to VCs, you sell it to bankers and analysts and people who want to keep abreast of mining. But so far, no one's done that. So hopefully someone on this call will take that business model and go do it.
So I think that was the last question. I will just ask the last ultimate one, which is how do you see the future of mining? Do you see it to be an industry that will still continue existing? How do you see the future of mining in the upcoming future?
Mining isn't going anywhere. So I think what's going to happen is Bitcoin isn't moving off proof of work ever. There is too much at stake. You have too many companies that are dependent on that mining piece. So it will become the poster child for a proof of work environment and a proof of work algorithm. Ethereum, meanwhile, will transition off proof of work at some point fully, and they will become the poster child for what a proof of stake network looks like. I do worry that there is going to be no more coins that can really compete on that level. I think that, you know, Zcash and Monero, etc., will have their own niches to be fulfilled, and they will keep to proof of work because it is easier to get users that way. It's easier to onboard new people. But, you know, I worry that there's going to be no coin that will become as big as Bitcoin or become as big as Ethereum. And because Bitcoin has become so big, it's going to start to attract more regulation, and through that, it's going to attract some of the more larger players. So we're already seeing this. You know, 2019 was the year of the business for Bitcoin. You had all of these large facilities migrating from China to the US. You had all of this infrastructure being built out. You had all of these companies pivoting from whatever else they were doing, focusing solely on mining. You even had companies starting to experiment now on alternate models of revenue. So the hotly talked about debate right now is transaction fees. Can we make a business model out of replacing the block rewards with transaction fees? BTC has an approach for that, and it's hotly talked about. There's another fork of BTC called BSV that has their own approach to that. BCH has talked about it. So all the different forks of Bitcoin are, you know, chatting about it. And I think that is going to end up causing a lot more specialization, and it's going to open the door to some really creative models. Mining isn't going anywhere. People keep saying it's disappearing. They've been saying that for 10 years. Cryptocurrency isn't going anywhere. As long as people continue to invest in the network, it will continue to be around.
Thank you very much. I see there are a lot of very thankful comments on the chat. Yeah, thank you very much everyone for coming, from Kristy for this amazing presentation. The video will be available on YouTube on our channel, Zero Knowledge. We have a Telegram group called ZK-Global where we post all our events and all the video and slides if available. And I will yeah, thank you again, Kristy, for spreading the word about this amazing and very little known aspects of blockchains.
Thank you for having me.
Bye, everyone.